First off, let's talk about clustering in general. So clustering is one of the tasks in machine learning, and it groups the data instances into multiple groups named clusters based on the patterns. So what does it mean? First off, you remember we talked about learning tasks in the last week, right? You remember? So we had supervised algorithms and unsupervised algorithms, right? And in supervised algorithms, we use labels, right? And these labels can be class labels or continuous labels. Do you remember discrete labels or continuous labels? For continuous labels, we had regression, prediction. For discrete labels, we had classification. Do you remember? And we said that when we don't have labels, that's unsupervised task, right? Unsupervised learning. And one of the unsupervised learning algorithm tasks is clustering. So it's a task, and it has different algorithms for this task. What is that? It's just grouping. We group the data into several clusters or groups, okay? And so we don't use labels. Now you might be wondering, then how do we group them? We look at their patterns, right? And this pattern can be anything, such as, assume we have images of objects. So the pattern can be shape of the object. Another pattern can be color of the object. So in general, the data points fall somewhere in the Euclidean space, right? The points which are closer to each other have similar patterns. The points which are very dissimilar from each other, they must be in different clusters, in different groups. Agreed? All right. So, okay, now clustering uses the patterns of data, as we said, and not any labels. Therefore, it is unsupervised. Agreed. Okay. By the way, when I say data instances, I mean data points, I mean data vectors. They're the same thing, right? Okay. For example, if we have a bunch of red apples, this microphone, red apples, green apples, and cucumbers, okay? Now you tell me, so I have red apples, green apples, and cucumbers are usually dark green, okay? Green apples are usually light green, bright green. So, and red apples. Okay, we want to cluster them. One might say, okay, I can divide them into two clusters, apples and cucumbers, right? Based on their shapes, because apples are round and cucumbers are sticky, right? Like sticky. They're thin. One might say, no, I want to divide them into three clusters based on their colors. Agree? So red apples, green apples, and dark green cucumber. Basically, I'm dividing the cluster of apples into two subclusters based on their color. So basically, if we assume in the space apples are here and cucumbers might fall here in the space, right? But if you look at the apples closely, you will see that. Can you guess the colors of these points that I just drew? Okay, of course, these are green, because these are cucumbers, right? So as you see, we kind of have two subclusters here for the apples. Is this one red apple or green apple? Most probably green, because they are closer to the cucumbers, which are green. Wow. So green cucumbers, green apples, and red apples, right? In the space, how they are distributed. So depending on which pattern to consider, shape or color, which one? Agree? Now, clustering is an ill-posed problem in mathematics. Do you remember? We talked about it in the last week. What does it mean? It means that we cannot determine the number of clusters at all. It's like a chicken and egg problem, kind of. Problem. Why? Because whatever I say it is in a cluster, someone might say, no, I see it as two clusters next to each other, right? Or multiple clusters. So it depends on the taste of people or algorithms, right? And by the way, clustering is an important task in mathematics as too, right? Even in pure mathematics, they have work. They have a lot of work on clustering in mathematics. So this is one of the parts that mathematics meets machine learning. Okay, where were we? So yeah, as I said, it's an ill-posed problem. In other words, it depends on the taste of the user. Now you might say, okay, so as it is an ill-posed problem, we should set the number of clusters, right? I want this number of clusters. So clustering algorithms have hyperparameters for the number of clusters. What do I mean by hyperparameter? Do you know that? If you don't know it, why don't you ask? Yeah. What is that?
I think it's a parameter that can't be derived from the data.
Yes, that's correct. What that's your
So like in application machine learning, hyperparameters is something which we tune our machine learning model with.
yeah, exactly. So basically, both said correctly. So we have hyperparameters and parameters in machine learning. Parameters are learnable. We learn them by optimization. Okay. Do you remember the learning task that we discussed in the class week? The learning task F. Do you remember? It had some parameters theta. We want to learn that parameters, those parameters. An example of parameters in machine learning is the weights of neural network, and we'll see that, right? We'll see that in this course later. So that's one thing. And what is hyperparameter? Hyperparameter is not learned. It's set by the user. We just set it to some value. Okay. And finding the best hyperparameter means cross-validation. I believe both Morteza and TA and also me at the end of the last session talked about cross-validation, right?
How would cross-validation apply to various hyperparameters? Because I believe it primarily introduces a way to randomize the test, train, validation.
Yeah, so in cross-validation, we divide it into train, test, and validation. And we use validation set for finding that which hyperparameter is the best for us. Right? Okay, so you change the hyperparameters, although this is out of the scope of this session, but let me say it briefly. I don't want to discuss it too much because it's out of the scope of this course. But anyways, assume we have a hyperparameter, okay? And this hyperparameter can get some values between 0 and 1, for example. Okay. Then I say for that hyperparameter h, getting the values maybe 0, 0.1, 0.2 until 1. So I divided it into several steps, okay? Several candidates for my hyperparameter. Which one is the best? Of course, it's a continuous hyperparameter. Okay, I don't like this microphone. One of the feedback was using microphone. But as you see, it has a problem. It's a technical problem of microphone. Okay, anyways, where were we? So, yeah, we have assumed the hyperparameter is between 0 and 1. It's a continuous value, right? But we need to make it discrete because we can't check it for all values between 0 and 1. We have infinite options, right? So we divide it into several cases, and then we have a for loop. Then inside this, then we have the for loop for k-fold, right? K-fold, K1 to 10, 10-fold cross-validation. Do you remember? And then inside that, I divide data. I already have divided data, and therefore I take basically k-fold as validation, and the rest as train. Right? We have split our data into 10 parts. In the first loop here, I take the first part as test and part 2 until 10 as the train. Then I go to the second loop. Then I get the second split as second part as the validation, and the rest of the 9 parts as a train. So basically, I'm rotating over the data. Okay, cycling over the data. And then what happens? And then what happens? So I train my machine learning model by train set, then test my machine learning model by validation set. It gives me some accuracy, some results, some performance, right? Therefore, we will have until here, up to this point, right? We have 10 accuracies, 10 validation accuracies, 10 validation errors, whatever we call them, right? Therefore, we can take the average of these 10 errors, right? As a result, here, for every H value, I have one average validation result, validation performance. Okay. One of them is the best validation performance. That would be the best H. Guys, I think except some people here, no one understood what I said. But if you didn't understand this, come to me after the class, because here I can't emphasize on this more because it's out of the scope of this session today, okay? But come to me, don't skip it. That was a general idea of how to use cross-validation for tuning hyperparameters. Just in parentheses, let me tell you that. Why don't we use test set for tuning hyperparameters? We don't use test set for tuning hyperparameters because that would be cheating in machine learning. Because when you are training, you are setting your hyperparameters, right? You're not supposed to have the test set. The test set will be available to you in reality. Test set will be available to you after deployment of your product. Assume you want to design some machine learning algorithm, some software for ministry. You design it, everything is done, you sell it, they install it on the traffic, maybe, intersections, and then the test set comes. When you were designing that, you didn't have a test set available to you. If you use test set for tuning hyperparameters, you will overfit to that, and you cannot generalize to actual unseen test data. That's why it's called cheating. You cheat yourself. You think that you're working very well, but in reality, it will work awful. Okay, so anyways, I close the parentheses. Now resume this session. So we have hyperparameter for number of clusters, or some hyperparameters which are not exactly the number of clusters, but they affect the number of clusters. So by tuning that hyperparameter, the number of clusters which are found is changed. You get it? Either implicitly or explicitly, they affect the number of clusters. Okay, one can set the number of clusters to be the consensus between most of the users. So you might say, which clusters, number of clusters should we use? And I will answer you. Let's see what is the consensus between the tastes of humans, right? Usually when we see a separate island in the space, we want that to be one cluster, right? So we can tune that hyperparameter to see which one gives us one cluster for that separate island. By what do I mean by island? Just a cloud of data points there, somewhere in the space. Okay, and we have surveys on clustering algorithms. You can see them, okay, in these references. Now, taxonomy of clustering algorithm. Okay, so we have. Let me very briefly tell you what is the taxonomy. Different groups of algorithms for clustering. Some of them are partitioning algorithms. What are they? So examples, K-means, basically, K-means divides the data set into K clusters. K is the number of clusters, okay, by assigning each data point to the cluster with the nearest mean, okay. I will explain this algorithm in a few slides, okay. K-medoids, which I will also explain in a few slides, is similar to K-means, but rather than mean, it uses medoids. What is medoid? I will talk about it. Medoid, just what is the difference between K-means and K-medoids? It is that K-medoids, in K-medoids, the cluster centers that you will return at the end will be one of the data points. In K-means, your cluster centers is not necessarily one of the data points. I will explain this in more details in a few slides, okay? Here, I'm just reviewing the taxonomy. We have fuzzy C-means. Fuzzy C-means is similar to K-means, but it uses fuzzy logic. Do you remember? I talked about fuzzy logic in a few sessions ago. But let me tell you what is the difference between K-means and fuzzy C-means. K-means basically says this data point belongs to cluster 1. That data point belongs to cluster 2. But fuzzy C-means doesn't say definitely with saying that it belongs to this cluster. It says no, 70%. It belongs to this cluster 1, 70%, 20% to cluster 2, and 10% to cluster 3. Do you agree? So it gives percentage of belonging to different clusters. So as you see, you can see K-means kind of as a special case of fuzzy C-means where we say 100% it belongs to this cluster, right? We have hierarchical algorithms. What is it? So it divides, as it's obvious by its name. We have hierarchy, okay? And we have two directions in the hierarchy, right? Either at first, we can assume we have a small clusters, we find some small clusters, and then we merge them. What do I mean? Assume I have these data points. Yeah, I will tell you. So these, assume you have these data points. Initially, I say this is one cluster, this is one cluster, this is one cluster. Then I come one step ahead in the hierarchy. I say, by the way, these are closer to each other. So I see these as one cluster and these are one cluster. So start with many small clusters and then gradually merge them so you have fewer number of clusters but bigger clusters. Okay? And as you see, you will have like a pyramid. You will have a hierarchy, right? And then you give the choice to the user which level of the hierarchy you want to be. That's exactly that hyperparameter for number of clusters, right? Depending on where we stand in this hierarchy, it changes the number of clusters.
Is the level of hierarchy you get out defined explicitly at the beginning, or can you run an agglomerative model and then with the output, like filter by level of hierarchy after the fact?
So basically, agglomerative algorithm, which starts from small clusters and builds up, it can start from every data point as a single cluster. Okay. Every data point is a single cluster. Then two data points which are close to each other, let them be one cluster, and you build up. I don't know. Did I answer your question or not? No.
Similarly, is the output of this model allow you to dynamically switch between the levels whenever you want, or does it output only one level in terms of clusters that you've specified beforehand? Like if you ran this,
Yeah.
could I say, give me the data split into 4 clusters just off the model that's already been trained, and then immediately after say, give me the model split into 8?
Yes. So it can build the clusters, the whole pyramid, the whole hierarchy, and then it says which level you want or which number of clusters you want. As soon as you say I want 4 clusters, then it can search which level corresponds to the 4th cluster.
Oh.
Yeah.
Actually, one more quick question.
Yeah.
Is this hierarchical algorithm, is this algorithm a deterministic algorithm? What I mean, if you would like build from single data point as a cluster to like one, the multiple times you would run the algorithm, every time you would receive the same data points in, let's say, 3 clusters, or each time you would form 3 clusters, different data points with.
So basically your question is whether it's a stochastic random. So we have some randomness in the algorithm or
same results for
let's
say 3 clusters.
So it's a family of algorithms. Even if we don't have any stochastic algorithm in this category, maybe you can propose an algorithm in this category and publish a paper. So these are families of algorithms, right?
Okay.
There can be stochastic, deterministic algorithms, anything. Okay. Also, the other way around is divisive. So divisive, sorry. Yeah. So we start with one big cluster. The whole data is one cluster, and then we make it a smaller. We split it into several clusters, several smaller clusters. Okay. And again, we have a pyramid or a hierarchy in the other way around. So we have density-based algorithms. The most famous one is DBSCAN, short for density-based spatial clustering of applications with noise, right? So what is that? Basically, it says it uses a density. And what's the advantage of DBSCAN over K-means? K-means, as we will discuss, it assumes that the clusters have Gaussian distribution. So they are like blobs, okay? But what if my cluster is weird, like a worm? So we have data points here. Then K-means will crash, will not work well, okay? DBSCAN is good, suitable for those cases when we have weird shaped clusters in the space, okay? It works on density. And optics, which is short for ordering points to identify clustering structure, it's similar to DBSCAN, but it gives more freedom, kind of, because it can handle varying densities. Because in DBSCAN, we'll set some hyperparameters, and that hyperparameter determines which density we want. But in optics, it handles dynamic density. Okay. By the way, we will cover K-means, K-medoids, and DBSCAN today. Also, we'll cover another thing too, if we have time. Okay, we have distribution-based algorithms. What do I mean? So, assume we have clusters of data in the space, right? You can see every cluster as some cloud of data point having some distribution. Do you agree? Having some probability distribution, probability density function, for example, right? Like Gaussian, like beta distribution, gamma distribution, right? If it is discrete data, like Poisson distribution, right? So we have different distributions. And I don't know if you are familiar with mixture models or not. What is that? So when we have, assume we have something like this, then we can fit one Gaussian distribution to this, assume it's in one dimension data, okay? But what if my data is like this? It seems that kind of we have two Gaussian distributions. Then this is mixture distribution because it's a mixture of two distributions. Okay, a combination, a mixture of two distributions. It's a summation of two distributions. You might note that when we have one single distribution, its integral is one. It integrates to one. It's probability density function. When we have two distributions, a mixture of two distributions, they integrate. They both integrate to one. So basically, this plus this becomes one. Okay, because it needs to be probability. Okay, and so GMM, short for Gaussian mixture model, is a special case of mixture models when we have a mixture of Gaussian distributions. Okay, and the most famous algorithm for finding mixture distributions, for fitting mixture distributions to data, is expectation maximization. Okay, and by the way, I'm not sure how much of these things we can cover in this course, but you can always find these things in my YouTube channel, right? Don't worry, we will cover enough in this course, okay? But for more interested students, I'm saying, right? You might want more. If we don't have time to go over expectation maximization or mixture models, you can find them in my YouTube channel in detail and theory, okay? So where were we? So as you see, if we fit a mixture distribution, then we have clustered data into several clusters. Agree? Agree. And yeah, where were we? Yeah, okay. Mean shift iteratively shifts data points towards the mode or peak of the data distribution to find dense regions. I think its explanation is obvious. So by the way, in distribution-based algorithms, we work on the modes of data because when we have several modes, we can fit a mixture distribution, right? Modes. So grid-based algorithms, example is STING, a statistical information grid. Basically, it divides the data into a grid structure, then groups points within the same grid itself, right? So a hyperparameter is the size of grid, how fine it is. Graph-based algorithms, spectral clustering is one of them, which is very interesting, and hopefully we'll cover it today if we have time. So basically, it uses the eigenvalues of similarity matrix to reduce the dimensionality, and then applies a clustering algorithm in the reduced space. What do I mean? So basically, it closely is related to dimensionality reduction, okay? And it uses Laplacian matrix of the graph. Okay, I don't know. Have you passed any graph theory course? No. Okay, we'll see. So it uses the Laplacian matrix in order to cluster data. Markov clustering, MCL, simulates random walks within a similarity matrix to discover clusters. So what do I mean? What is random walk? Assume we have a graph, okay? Then I randomly walk from every vertex to an adjacent vertex, right? And I can do it probabilistically. So it's a random algorithm, okay? And that's random walk. When you walk through the graph randomly based on some probabilities. And they do that for finding clusters. Self-organizing maps, or SOM, basically it is a neural network, one of the very first neural networks in the previous century. It's very old, okay? To map, that's also used for dimensionality reduction. So we have high dimensional data, we map it to a low dimensional space, and in that low dimensional space, I cluster data. Okay, okay. Ensemble clustering, what is that? It combines multiple clustering results, so we use an ensemble of algorithms. These algorithms that we talked about, you can have voting between them, right? One algorithm says this belongs to cluster 1. The other algorithm says no, I believe this belongs to cluster 2. So we will have a democracy. Majority vote between the algorithms. Yes.
How does it work with fuzzy logic that doesn't say that?
Yeah. So if you then you can have several fuzzy algorithms. This says I believe with 70% confidence it belongs to cluster 1. The other says no, I believe in with 65%.
But you can like mix and you can have a fuzzy.
Yeah. So it depends on how you model your ensemble. Okay. When you have ensemble, you listen to everyone in that every algorithm that you have in that ensemble. By the way, theoretically, it can be proved that ensemble learning reduces the variance of estimation. Okay. For proof, you can see my YouTube channel. By the way, I know what is in your mind. Sometimes you might think that he refers to his YouTube channel a lot. I refer it to only for interested students, not required for the course. So you shouldn't be worried, right? For interested students, feel free to see the proof in my YouTube channel. Okay. Meta-heuristic-based clustering. So it uses meta-heuristic optimization that we talked about. Do you remember? Intelligent search. We talked about. So you can use intelligent search to find the clustering algorithm. That was just a taxonomy. Now let's go to the example, to the clustering algorithms, basic ones. Let me go through these very fast to start a spectral clustering, which is more important, I believe. K-means. This is the easiest, dumbest algorithm for clustering that even a primary school student can find it out. Okay, how to do it. So it says that I have some data points. Okay, basically I have some data instances, x1 to xn, each of which is d-dimensional. Okay, in the d-dimensional Euclidean space, right? The number of clusters k is given by the user, so you need to set it. That's one of the flaws of this algorithm, right? And then you initialize the cluster centers in the input space randomly. So you see in the input space what is the domain, acceptable domain of your data, and in that domain you initialize your cluster centers. Not necessarily it shouldn't necessarily be one of the data points, right? So we have k cluster centers randomly in this space. Then until convergence of cluster centers, because we are going to move the cluster centers, right? We are going to move them iteratively. After some iterations, they don't move a lot significantly anymore. So first we assign the data instances to clusters, and then we refine the cluster centers, as you see, alternatively. We say that, okay, based on the cluster centers that I have, what are the labels labels of prediction for data points? Then I refine the cluster centers. Then I label the data points again. Then I refine the cluster centers. You see how we alternate? So for assigning the data instances, we have some cluster centers, right? Then we see for every data point, we see what is, so we calculate the distance of that data point from all of the cluster centers. The minimum distance tells us which cluster it belongs to. Do you get it? So as you see, arg mean over J. J goes from 1 to K. So I have K clusters, right? What is this? This is Euclidean distance, L2 norm, Euclidean distance between Xi, my data point, and Cj, my jth cluster center. As you see, I have a for loop over the data points, x1 to xn. It gives me Li, the label for the Xi, and Li is a scalar, integer, 1 to K, right? You might be wondering why Euclidean distance. You can use any distance that you want. Usually we use Euclidean distance. You can use L1 norm distance, whatever, okay? But when you change the distance metric, you will get a slightly different results. Okay? Then you refine the cluster centers, or you tune them. So for each cluster 1 to K, then what do? Now that you have labeled the data points, so some data points belong to cluster 1, take the average of them, let the new cluster center be that average. Did you get it? Yes. As I said, you can use anything. Squared Euclidean distance or Euclidean distance. This is Euclidean distance with a square root. If you use a squared, then it will be without square root. By the way, this is L2 norm. This is a squared L2 norm. Didn't you watch the preliminaries? I told you, please watch it. Please watch it. I have explained all of these in the preliminaries. Okay? Please watch the preliminaries. That's crucial for what I teach. Okay? Otherwise, you might not understand what I'm saying. So where were we? And then we take the average of the instances with Li equals J. So the data points that are assigned to the Jth cluster as a Cj. And we do it, at the end, we return the cluster centers and the data labels. Okay? Example is this. Do you agree that after convergence, we are partitioning the space? Right? So basically, we say that all of the points which fall here belong to cluster 1. All of the points which fall here belong to cluster 2, etc. We are partitioning the space. Yes. The algorithm will converge as long as you initialize the cluster centers in the domain of your data.
Yeah, but how do we know that it has converged?
First off, it has some convergence proofs, but even intuitively, it's obvious because of this. Always you take the average of, for tuning the cluster centers, you take the average of cluster points, right? So here we are using, we are assigning every point to this closest cluster center. And then we tune the cluster centers to be the average of the data instances assigned to that cluster. I believe to me, intuitively, it makes sense. But it has a theoretical proof too for convergence. Okay. So that was K-means. K-medoids. So one problem with K-means is that its cluster centers are not necessarily one of the data points, like this. Here is not one of the data points, right? If sometimes in some applications, I want the cluster center to be one of the data points, okay? Then in this case, I can use medoid. What is medoid? Medoid is a representative data instance for a group of data instances whose sum of the similarities to all objects in the cluster is minimal. So basically, so I have a cloud of data points. Which of these data points has smallest distance to other data points? Distance or dissimilarity. Okay. For example, here I'm saying that the smallest summation of Euclidean distances to all other points.
In both K-means and K-medoids, how do we handle ties between distances?
How do we handle ties? That's a good question. I think randomly you can get one of them. Okay. Because that will be on the boundary. And I think that doesn't make a huge difference. Boundary between two clusters. Okay, now in this case, then we'll have the center will be one of the data points. Now, one might say, although I think this needs to be rephrased a bit, but listen to me and I explain it correctly. Okay, so assume one might say, why can't I, if I want the cluster centers to be one of the data points, I can say I run k-means, and at the end, I find the closest point in the cluster to that cluster center. I will say you can do that, but that will not be equivalent necessarily to K-medoids. Why? Because in K-medoids, at every iteration, I'm finding the medoid as a center. But what you suggested, you do it only at the last iteration. Okay. Okay. So that's one thing. That's K-medoids, and the only difference is this: we get the medoid for tuning the cluster centers. Okay. DBSCAN. So K-means and K-medoids are effective for blob clusters. What do I mean by blob? I mean like this. Like they're like a blob of data, right? But what if it's weird? Okay. In this case, they will crash. They will not work well. So assume if you apply K-means on this, just give me. If you apply K-means on this weird worm thing, it will say this is one cluster and this is one cluster, for example, right? Because this is like a blob here and here like a blob. Yes.
Sorry, for the initialization part, for the initial guess.
Yeah. Sorry. For K-medoids, for initialization, also you need to initialize the cluster centers to be one of the data instances. But for K-means, it needs to be only in the space of data, input space, in the domain of data. Okay. So DBSCAN is good for weird shape clusters. It was proposed in 1996. Now you can imagine how K-means is old. How old it is K-means. So DBSCAN is useful for discovering clusters of arbitrary shapes. Also, it handles noise and outliers. Okay. So K-means also is not robust to noises much, but DBSCAN is. So basically, it says that some of these data points are noise and they don't belong to any cluster. DBSCAN does that. Okay. It is a density-based algorithm. It defines clusters as areas of high data point density. Okay. Separated by areas of low density. So between clusters, we have low density, right? DBSCAN finds out the number of clusters by itself. That's interesting. But although the number of clusters depends on the hyperparameters. So it doesn't have any hyperparameter explicitly for the number of clusters, such as K-means, right? But it has some hyperparameters which explicitly impact the number of clusters. So hyperparameters are epsilon and mean points. So epsilon is the radius that defines a neighborhood around a data point. Okay. And mean points is the minimum number of data points required to form a dense region. Okay. So basically, for every data point, I assume it has some neighborhood, some hypersphere around it with radius epsilon. Okay.
If we're finding our distances as a radius around a point, why is it better at snakes than the other?
We'll see. We'll see. So because here, for example, in this snake, I see for this head of a snake, I consider some neighborhood and I see these are in this neighborhood. Then I do it recursively. Then for this point, also these are in the neighborhood. Then for this part, these are in the neighborhood. So as you see, I can go along the shape, the snake, right? Because it does it recursively. Okay. So minimum number of points it determines how much density I want inside this neighborhood. To say that it's dense, yes.
We have to put in the number of clusters. So DBSCAN finds it automatically.
The number of clusters, no, they're not. So when you change epsilon and mean points,
Yeah.
it changes the number of clusters.
Oh, okay. But we don't put in a number of clusters.
No, you don't give the number of clusters. Yeah, no problem. So basically, these kind of say how much density matters to you. Okay. Types of data instances in DBSCAN. So some of the points are core points, some of them are border points, and some of them are noise or outlier points. So core points, as its name is obvious, a data point is a core point if at least minimum number of points are within its epsilon neighborhood, including itself. Okay. Border point is a data point which has fewer than minimum number of points within its epsilon neighborhood, but it is reachable from some core point. For every point, we calculate its neighborhood and we count the number of points in its epsilon neighborhood. If it is greater than or equal to minimum number of points, it's a core point. If it is less than that, but it is already in the epsilon neighborhood of another core point, then we call it a border point. The third case is that it has fewer number of minimum points and it's not even in the epsilon neighborhood of a core point. Then that would be an outlier. Okay. So this is the algorithm. We have data instances and then, sorry about the data instances and the parameters, epsilon and mean point. Okay. Then we initialize. Yes, just give me a second. Sorry, when I was preparing the slides, I copied and pasted and I forgot to delete these lines. I apologize. Okay. Yes. So DBSCAN is this. In this algorithm, it's an iterative algorithm. We go from one point to every point. So we check all of the points, okay, until all of the points are visited. Have you passed any algorithm or data structures course? It reminds me of search algorithms in graphs, like breadth first search and depth first search. Okay. Anyways, in parentheses, I said that. Okay, so we want to check all of the points until all of them are visited. Okay. So then we consider an arbitrary non-visited data point xi. Okay. Then, if the xi is a core point, we can check, right, by its neighborhood. We can check how many points are in its neighborhood. If it is a core point, then we make a new cluster. Okay. Then we add all of the points in the epsilon neighborhood of xi to that cluster. Okay. Then we recursively add the epsilon neighborhood of points in the cluster to that cluster. So basically, what do I mean? Assume this is a core point. It has a lot of points in it, in its neighborhood. Then this is a neighbor of this core point. Agree? Again, so I say this is cluster 1, belongs to cluster 1. This, as a result, also belongs to cluster 1. Then this itself has some epsilon neighborhood. Then I assign all of the, if it is a core point, then I say its neighbors also belong to this cluster, the same cluster, right? I continue until it becomes a border, right? So I continue this recursion until it becomes a border point. If it is a border point, Then assign xi to the cluster of these core points. Okay. Now, you tell me. Here, I never talked about noise points, right? That's the beauty of this algorithm. It says that those points are noise. I don't assign them to any cluster. So, for example, assume in this shape, weird shape, but I have a lot of points here, and I have 1 point here. It will say this is noise. I don't care. It's and it's neither core point nor border point.
Do we need the else if xi is a border point? Wouldn't every border point be assigned in the recursive step after the core point?
Yes, but the reason that I have said it because here this is the if for core point. Yeah, I understand what you're saying. But if you understand the algorithm, you can implement it as however you want. The algorithm is this. It's a recursive algorithm. Okay, forget this pseudo code that I wrote here. Just listen to the algorithm. We start with every point. If it is a core point, then we consider its neighbors. For every neighbor point, also have an epsilon neighborhood. Do you agree that it's a recursive algorithm? I do it until I reach the border. So the whole thing is one cluster, right? Now I might have 2 snakes, right? That's exactly where this while is. Okay, I go for the next cluster, then it becomes cluster 2. I do it recursively again. So I find all of the shapes, all of the clusters. Now that's why DBSCAN works very well for the 2 moons data. But K-means doesn't work well for that. Okay? Yes.
So where does this algorithm suffer compared to other algorithms? Is it just
So I think I believe that if your data clusters are Gaussian, the best algorithm is K-means because that's the fastest. Okay, this is not that much fast. Yes.
Can you have 1 core point per cluster, or can you have more than 1 point, core point per cluster?
No, I believe we have a lot of core points in the cluster. Because here all of these points, the snakes are the core points.
Doesn't it have to be 1 core point, because a core point defines a new cluster? But it doesn't matter what the core point is, because it will make the same cluster regardless.
I think you are confused with this sentence, right?
Yes.
Yeah, I think maybe you can drop this line. Sorry about that, but did you get the idea? Did you get the idea of what I'm saying? You can implement it in any pseudocode that you want. Did you get the algorithm? Okay, they got it.
The condition to be a border point.
The border point. So a core point, it has more than minimum number of points in its neighborhood around. So basically, it's in the middle of the shape. It's in the dense area. But border point is at the border, as its name says. And what does it mean? In its neighborhood, it has less than minimum number of points. Because, for example, this is the snake. This is a border point. This is the neighborhood. Only these points are in its neighborhood. Border of the dense area. Yeah. Yeah. Yeah.
Cluster can have multiple core points, so when you distinguish different clusters, how does it know it's a different?
Because that sentence that I wrote was because of that. Okay. So here, when we go inside the recursion, you shouldn't do this. Okay. That's why I believe that this pseudocode should be revised. But at the start of recursion, only if it is a core point at the start of recursion, make a new cluster. When you go inside the recursion, don't make a new cluster.
So you would make another cluster once.
Because here you start from here, for example, and you go inside the recursion in the same cluster. You finish this snake, then all of these points are visited. Now you go to an unvisited data point. That unvisited data point might be outlier. You ignore it. Don't do it. Do anything about it here. One of them might be inside another snake. Then you make a new cluster and you go inside the recursion again. Okay.
Snakes are colliding at some small points. or something.
So the question is, what if the two snakes are close to each other? Then if you change epsilon and minimum number of points, depending on that, it might consider both snakes as one cluster or two clusters. Okay. So this is an example. For example, it starts from one of the points, then it builds up recursively, as you see. Then it finishes this snake, then goes to this snake, and then this snake, and then this snake, and the rest, like these, will be outlier. If we change minimum number of points and epsilon, maybe some of these outliers will become inside the cluster, right? Okay. And these are the references. Now let's go to the next slide deck. Any question? A spectral clustering. So first, let's talk about Laplacian matrix. Okay. Listen, assume we have a data set x1 to xn. Okay. Don't worry, I will explain everything. I will build from scratch. We have a data set x1 to xn. Then we have in a spectral clustering and related algorithms, one of the related algorithms is Laplacian eigenmap. Okay. Anyways, we first construct a nearest neighbor graph. What is nearest neighbor graph? There are two versions of constructing nearest neighbor graph. One of them is graph of using epsilon neighborhoods. So nodes I and j. By the way, when I say nodes here, I mean like you can consider data points as nodes, graph nodes. Okay, nodes I and j, or xi and xj, are connected if their squared Euclidean distance is less than or equal to some epsilon. Do you agree? Okay, so basically they are in the epsilon neighborhood of each other. Or we can calculate k nearest neighbor graph. Okay, what is that? Node j is connected to node I if xj is among the k nearest neighbors of xi. So basically I can calculate the distance of all of the points from xi. Then I can sort the neighbors based on the distance. The k neighbors with the smallest distance to that xi are the neighbors of that xi. Right? I sort them in ascending order of distances. Okay. So two ways to make the k nearest neighbor graph. Then using the nearest neighbor graph, we construct an adjacency matrix. What is that? It's also called weight matrix or affinity matrix. What is that? It's a weighted version of nearest neighbors graph. Okay. So what is a weighted graph? A graph has some vertices and some edges, right? For example, this is a graph. These are vertices and these are edges. Agree? These edges can have weights between them, on them, right? Then it will be a weighted graph. Okay. What is a tree, by the way? A tree is a graph without any loop. Okay. So where were we? The weights of adjacency matrix represents a similarity of nodes. So basically, if 2 points are similar to each other, they will have more weight. If they are dissimilar to each other, they will have less weight. Because 2 points might be neighbor of each other, but very close to each other or a bit far away from each other, right? So we have the more similar, the more weight. Let W be n by n. Do you agree that the adjacency matrix should be n by n? N is the number of points. Because we need to see which points is connected to every other point, right? Or not. N by n. So it's ijth element, ith row, jth column. Is this. If xj is one of the nearest neighbors of xi, then we'll have the weight wij in that element. If I equals j, so it's on its main diagonal, I put 0 because I don't want to say every point is its own neighbor. Okay. If xj is not one of the neighbors of xi, then I'll put 0 because they are not neighbors. As you see, it's usually a sparse matrix, especially if k is small. Okay, now an example of the weight function. So now let's talk about wij. Of course, it should be some measure of similarity, right? So one of them is radial basis function or heat kernel. Here is the formula for that. Wij is exponential. So it's based, what is this? You tell me, guys. This is Gaussian distribution. A scaled Gaussian distribution with variance sigma squared, right? This is a scaled Gaussian distribution. Feel free to look up the PDF of Gaussian distribution. It will be similar to this. And it's called, that's why it's called radial basis function, another name for Gaussian distribution, okay? And we can use different functions. Usually we use kernel functions for that. I will talk about kernels later in this course, but let me tell you that kernel functions are some of the functions used for measuring similarity between the data points. Okay, this is one of them. And another approach is we say, let it be binary, wij. If I and j are connected, are neighbors, let it be 1, otherwise 0. Okay? So now Laplacian matrix. We define the Laplacian matrix of the adjacency matrix denoted by this L. So where did we start from? We have a graph. This graph has some adjacency matrix, and this adjacency matrix has some Laplacian matrix. Okay? So we have Laplacian matrix, which is n by n, and I define it to be, this is Laplacian, L. Laplacian is n by n, W was also n by n, D is also n by n. Okay? I talked about W already. L, I'm defining it here. And what is D? D is a diagonal matrix, which is called degree matrix. Its ith diagonal element is this. Di is summation of wij over j. Basically, Di is the summation of ith row of W. So let me say, this is W. Assume this is my W. It has some rows, agreed? I sum all of the first rows. I put it as the first element of D. I sum all of the second row in the W. I put it as the two-tooth element of D. The third row, I sum them up. I put at the third element of D until the end. Yes.
So we will have just the value of some.
Yes.
Rows.
Yes, exactly. D is a diagonal matrix whose values are the sum of the rows of W. Now, degree matrix minus W is called the Laplacian matrix. The row summation of the Laplacian matrix is 0 because of this, because I'm saying that D minus W. The row summation of Laplacian matrix will be 0.
Is there a reason we use the rows to determine?
This is definition of Laplacian.
Would it work equally well? Yeah, because D is just meant to be an arbitrary evaluation of how many neighbors a specific,
So
like how good.
it's a summation of weights corresponding to the ith node.
Yeah.
You can see it in this. We shouldn't consider about columns. Do you know why? Because columns are talking about being neighbor of the other one. Rows are saying that they are data points. Columns are neighbors of other data points. Okay, so now also there are some other variants of Laplacian matrix, such as this. D to the power minus alpha. W d to the power minus alpha. D to the power minus means inverse of matrix, right? And alpha means the power. Alpha is greater than or equal to 0. Usually it's half, like this. This is also sometimes called the normalized Laplacian matrix. Okay, and according to this paper, equation 8 leads to having the ijth element of the Laplacian matrix to be this. Wij over square root of dii djj. Okay. As you see, it's kind of normalized. Okay, where were we? Okay, now in linear, so this Laplacian matrix has some interesting characteristics in linear algebra. In linear algebra and graph theory, we know that if a graph has k disjointed connected parts, what do I mean? K parts, right? Its Laplacian matrix has k0 eigenvalues. First off, what do I mean by k parts? Do you remember we formed the adjacency matrix? So we change k based on, by changing k, you change the number of parts. Do you agree? If you set k to be large, you will have the whole data as one graph. If you make k smaller, for example, like this, these are the data points. Initially, by setting k large, all of the points are neighbors of each other. You make k smaller, it becomes two disjointed graphs, but with one single adjacency matrix, right? You will have one adjacency matrix for the whole graph, but it is disjointed, right? So here I have two parts, two disjointed parts. As a result, I will have two zero eigenvalues for L, Laplacian matrix. So Laplacian matrix is a matrix. You can calculate its eigenvalues. How many eigenvalues will equal to 0 will it have? It will be the number of disjointed graphs, subgraphs in the data, which will be impacted in the adjacency matrix. So the number of parts will affect the adjacency matrix. The adjacency matrix affects the Laplacian matrix. Therefore, it affects its eigenvalues. Okay? If you don't know what eigenvalue is, I have already explained that in the preliminaries. Okay. So we assume that the nearest neighbor's graph of data is connected graph. So we set k in a way that I will have the whole graph connected to each other. At least one edge will be here, right? In this case, according to this theorem that I just told you, I will have one zero eigenvalue for the Laplacian matrix because I will have one part. Agreed? So in spectral clustering and related methods, we ignore the eigenvalue corresponding to the zero eigenvalue. The result, because we are gonna work with the eigenvectors and eigenvalues of Laplacian, and we know that one of them will have zero eigenvalue. We'll ignore that. Okay? Now we start a spectral clustering. So what is a spectral clustering? It is a clustering method whose solution is reduced to an eigenvalue problem. Okay? So whenever, by the way, in machine learning, whenever we say it is a spectral algorithm, usually its solution reduces to eigenvalue problem of some matrix. Okay? And usually it has a geometrical approach. So a spectral algorithm has a geometrical approach and usually reduces to eigenvalue problem. Okay. Refer to this for a survey on initial work on spectral clustering approaches. By the way, I have tutorial paper on spectral clustering. Feel free to read that. A list of some initial works are these on spectral clustering. The general idea of a spectral clustering is this. This is important. General idea. What is that? First, we transform data from its input space, the space where it is in, to another low dimensional subspace. So it kind of uses dimensionality reduction so that the clusters of data become more separated, hopefully. Then we use a simple clustering algorithm in the embedding space, in the low dimensional space. So the idea is this. Do you remember I told you about K-means? It says rather than applying K-means in the input space, transform data to a low dimensional space. In that low dimensional space, the clusters get separated better, and then apply K-means in that low dimensional space. Did you get it? So as was explained before, now we need to talk about cut. As was explained before, we compute the adjacency matrix and its Laplacian matrix, right? We denote the graph of data set as this. Graph of data, right? Data instances, data points are x, right? I from 1 to n. These are the vertices of the graph. And the weights. These are the weights, wij, right? The weights of the between the xi and xj. Agree? Now let the data points be divided into two disjointed clusters, A and A prime. Okay? So assume my data is a union of A and A prime, where A and A prime don't have any overlap. Okay? Basically, I'm dividing my data points into two parts. We define the cut between two subgraphs as this. This is a definition, right? Cut between A and A prime is a double summation over wij, over I and j. So I belongs to A and j belongs to A prime. Okay? Now, do you understand what is it? It is basically assume this, I have two subgraphs like this and this, right? Between these two subgraphs, I might have some edges. Okay? They have some wij. Then basically, I'm summing over all of these wij's. I is from A, J is from A prime. Okay? And this is called the cut. As the summations can be exchanged, because I can exchange the summations, cut A and A prime equals cut A prime and A. Right? Now, if the two clusters or the two subgraphs are very different or far from each other, okay, then the summation of weights between their points is a small. Do you agree? Because they're very away from each other, wij between them is very small because wij is a measure of similarity. So the cut will be small. Agreed? Hence, for finding the separated clusters, we can find the subgraphs which minimize the cut. So, as I said, two clusters are very far away from each other if the cut becomes a small, right? So let's minimize the cut. As you see, it became an optimization problem. Okay? So minimize the cut over A and A prime, which was this. This was the cut. Agreed?
We do cut more than two, and we do cut with an arbitrary number.
Yeah. We'll talk. So assume here we are talking about two graphs, and we'll extend it. Okay, to multiple class. However, this minimization is sensitive to outliers, right? Why? Because an outlier can be seen as one cluster which is far away from others. So when you minimize the cut, it will say one of that outlier is a perfect cluster, separated cluster, because its wij is minimized from other data points because it's outlier, right? So to overcome this issue, we use a normalized version of cut named ratio cut, okay, which is defined as this. Ratio cut between A and A prime is this, okay? What is this? Cardinality of A, set A, and cardinality of set A prime. Cardinality, the number of points in A, the number of points in A prime, okay? And according to equation 13, so I can write this as this. I changed the order, okay? Now, minimizing the ratio cut rather than the cut resolves the problem with outliers because the cluster of, because I think it's, so now let's see the reason. Why does it resolve the issue of outliers? And here I explain. Because the cluster of outliers is a small cluster, right? An outlier can be a cluster of 1 point, for example, right? It's a small cluster and its cardinality becomes a small. When its cardinality becomes a small, it will blow up the normalized cut. because the denominator will be small, the fraction becomes very large. And we want to minimize the ratio cut. Did you get it? Okay, now we minimize the ratio cut. Theorem. Minimizing the ratio cut, that is equation 16, is equivalent to this. Minimize summation of wij fi minus fj squared over f. This is the vector of f, n dimensional, f1 to fn, where fi is defined as this. If I belongs to A, fi is this. If I belongs to A prime, fi is this. Please refer to my tutorial paper or my book for the proof and read the proof. When you read the proof, you will see the beauty. Okay. Here we don't have time to go through the. Oh, we have. Okay, I have provided the proof. I forgot. But you can read the proofs also in as well as the book. I forgot to that I had put the proof here. Okay, so let's see the proof. So here is the cost, right? Here is the cost. Summation wij fi minus fj squared. So I replace fi and fj with their definition that we had here. Okay. Then what happens? So this is, you tell me. Now I separate this summation into 4 parts. Do you agree that I can be in A, J can be in A prime, I can be in A prime, J can be in, so I can be in A, J can be in A, I in A prime, J in A prime, I in A, J in A prime, I in A prime, J in A. 4 cases, right? So now, according to this definition and these conditions, I replace fi and fj. Okay, so I will have this. In 2 of them, this will be 0. Okay, fi minus fj will be 0 in 2 of them. Then I will have 2 parts, which are these. Okay, now these two minuses will go away because of this square. Okay, as you see, don't have it here, and the rest is as before. Okay, now I use the binomial theorem. A plus b squared is a squared plus b squared plus 2ab for these two. Okay, agreed? Agreed? Now what happens? These 2 parts are equal to each other and they don't depend on I and j. So I factor them out and bring them out of the summation. I will have this. Okay? Now what happens? What is this, guys? This is the definition of cut. This is also the definition of cut. So I will have cut A and A prime and cut A prime and A. Okay? We know that cut A and A prime equals cut A prime and A. So it will be 2 of the cut A and A prime. Agreed? I can replace these 2 with this summation. A over A, cardinality of A over A, which is 1. Cardinality of A prime over A prime, which is 1. 1 plus 1 equals 2. Right? Then I combine the 2 fractions. Combine 2 fractions based on their denominator. Okay. So I will have this and this. So this, I combine this with with this, and this with this. Okay. I will have these 2 fractions. Now what happens? What is cardinality of A plus cardinality of A prime? It will be the cardinality of the whole data, which is n. Likewise, this will be the whole data n. Okay. Now I factor out n. I will have it here. Okay. And I multiply this cut to the fractions. I will have this. Okay. What is this, guys? That was exactly the ratio cut that we defined. So we just proved that QED. We just proved that in this course, what if either I don't explain the proof, or if I explain the proof, I will go step by step. Okay. So as we just proved that here, the minimizing this equivalent to minimizing the ratio cut times 2n. 2n is this constant scalar, right? Another theorem. This, you can write it in this form, in vector form, using the Laplacian. Interestingly, in the left-hand side, I have the adjacency matrix. In the right-hand side, I have the Laplacian of the adjacency matrix. F transpose LF. F was the vector of F's, F1 to Fn, right? L is the Laplacian matrix, right? Proof. Let's start with the right-hand side. F transpose LF. Replace L with D minus W with its definition. Okay. Now I multiply the terms to each other. So I will have F transpose DF minus F transpose WF. Okay. Then I write them in a scalar form, right? So I will have element-wise. Summation of di fi squared, because this is quadratic with respect to f. We have f twice, fi squared di, and also this summation, double summation of wij fi fj. Okay. By the way, why is this double summation but this is one summation? Because d is diagonal. D is diagonal, but w is not necessarily, is not diagonal. Okay. Now I can say I can multiply it by half and multiply it by 2 again. Okay. Now I write these two summations as summation plus that summation. Okay. Now what happens? Now I replace di with its definition. What was di? Summation of wij over j. Summation of rows. Do you remember? So I will have this. And this is the third as before, right? Now you tell me. Now wijc, this step C notices that wij equals wji, right? Because we usually use symmetric similarity measures. We usually use for example, the RBF function that we used for wij, do you remember? It was symmetric for x and xj. So as a result, I replace wji with wij. Okay. Now I use the binomial theorem again. A minus b squared is 8 squared plus b squared minus 2ab. I use the reverse binomial theorem. I'll get this. I just proved that. QED. Okay. Now you understand that why in clustering, in spectral clustering, we minimize this. Because minimization of this is equal to minimization of this, and minimization of that equals to minimization of ratio cut. Right. And ratio cut was also robust to outliers. So now we minimize this subject to the definition of fi that we had for all I from 1 to n. Right? So it's a constraint optimization problem. This is a very complicated problem to solve. It's very hard, okay? Especially because of the constraint. So what do? We can relax the constraint to have orthonormal vector f. We say, let's relax this and we assume that the vector F is orthonormal. Okay. So I change the constraint to be F transpose F equals 1. Its length is 1, right? And yeah, its length is 1 and it's an orthonormal vector. Okay. So just give me a second. Here, note that Fi for if I was in A, Fi was positive. If I was in A prime, Fy was negative. Okay. Yes. Here in the modified constraint, we keep the sign characteristic of equation 18, at this one. So we use this. And this modification satisfies this constraint. Do you agree? Do you know why? Because Fi is either positive, so Fi times Fi is 1, positive 1, right? Or if it is negative, minus times minus is also positive. So the sign is also +1. Okay. So why did I say that? To make sure for you that, to assure you that this relaxation is valid. This relaxation is valid. Do we have time? No. Okay. We will cover the rest of this in the next session. So we talked about Laplacian matrix in the previous session. We said that we have the adjacency matrix for showing how the points are close to each other or neighbors of each other, right? And so the elements of the adjacency matrix measures the amount of similarity of the points, right? And then we also said that we can have the Laplacian matrix for the adjacency matrix, which is defined as the degree matrix, as in equation 5, minus the adjacency matrix, which is W, right? So Laplacian matrix is equation 4, and the degree matrix is basically a diagonal matrix whose elements are the summations of the rows of the adjacency matrix, right? And we also said that we can have normalized Laplacian matrix as discussed in this slide. And then we said, according to linear algebra and according to graph theory, so the number of, if a graph has k disjointed connected parts, then the Laplacian matrix has k zero eigenvalues. This is one of the properties of the Laplacian matrix. Okay. So then we said, we assume that we set k, or we measure the adjacency matrix in a way that we want the graph to be connected. Someone asked at the end of the class, the previous session, that what is the difference between a connected graph and a fully connected graph? You know the difference? So here, when I'm saying that we assume that we have only one part, I don't mean that it's a fully connected graph. Fully connected graph, or also called complete graph, means that all of the nodes are connected to each other. Okay. All points are neighbors of each other. So if you set k to be n, the number of points, then that happens, right? But one part graph, it means that, for example, this is an example. This is a one part graph, right? It's only have one part. It's not disjointed. But a fully connected graph would be something like this. Okay, that's the difference. And now, then we said, so we started the spectral clustering. We said that what is it? The main idea behind the spectral clustering is that let's find the subspace. We go and project data onto the subspace. We reduce the dimensionality in the embedding space, in the subspace. Hopefully, the clusters become more separated from each other in terms of their patterns, right? And then we apply a simple clustering algorithm such as K-means in that subspace, right? Right. And we defined cut. What was the cut? So we said graph, assume we have a graph of data X and W, where X is the data instances, or data points or whatever we call them, we can see them as the nodes of the graph. And the adjacent, the Wij's, the elements of the adjacency matrix, you can see them as the weights of the edges, right? And then we said, so what is a cut? A cut is defined as equation 12, where it's a summation between summation of the weights of the edges, where one part of the edge, one side of the edge is in one part, and another side is on the other part. So again, the whole thing is connected. The whole thing is connected, but these are two clusters. These are two clusters, and there is a small Wij between them. How do we find the small Wij between them? We minimize the cut, right? When we minimize the cut, basically the algorithm finds the Wij's which are small. In other words, it finds the clusters, right, which are separate from each other, right? Because if Wij is large, it means that we are inside the cluster. We are not between two clusters, right? Right? So, but feel free to interrupt me, okay? Whenever you have any question, you don't need to raise hand, shout at me, okay? So, yeah. Yeah, I believe we minimize it. We minimize the cuts because we want to find the separate clusters, right? If we maximize it, we will basically find the cusp, the Wij's which are inside the cluster, because inside the cluster the points are close to each other, right?
Why is Wij larger for shorter distances? Isn't it more common to?
Wij is a measure of similarity. It's a measure of similarity. As a result, the less the distance, the more similar they are. So then, as I said, we minimize the cut. Equation 14, and we did here is a definition of the cut, and then we said there is a problem with the cut. And what is that? So going back to the definition of the cut, if we minimize this, what happens for an outlier? Then in this case, an outlier which is far away from all the data points will become one cluster with single point, right? One single point will become one cluster, where its Wij is very small from other points. Agree? So that's a flaw, and we don't want to consider every outlier as one single separate cluster. In this case, for tackling this problem, we define ratio cuts, which kind of normalizes the two cuts with the cardinalities of the sets, right? And in this case, for an outlier, one of these fractions will blow up. When I say blow up, I don't mean becomes infinite. It means it becomes large. So, for example, for an outlier, this cardinality of A prime might become 1. But if it's not an outlier, it's inside some cluster, big cluster, the cardinality of A prime might become 100. So when we have 1 in the denominator, the fraction becomes larger compared to when we have 100 in the denominator, right? Yes.
So you're saying it's 1 for all cluster or
So,
an outlier?
For an outlier, how many outliers do we have in that? For example, assume this is here it is, and this is an outlier. Then the cluster size will be 1. Or even if we have 2 outliers next to each other, it will be 2. It will not be 100, because if it is 100, then it would not be an outlier. It would be a separate cluster. It would be an inlier, right? So that's the thing, and that's why we minimize the ratio cut, and then we had 2 theorems. First, we said let's minimize the ratio cut, and we said that minimization of ratio cut is equivalent to minimization in equation 17, where we define Fi as in equation 18. We proved that here, and here was the proof of why those 2 minimizations were equivalent. And then we said, by the way, we have this equation 19 too. So minimization of the left-hand side is equivalent to minimization of right-hand side, right? And here it is. We proved that. So as a result, in equation 20, we said that let's minimize F transpose LF subject to the definition of Fi, right? So the whole thing basically means is equivalent to minimization of the ratio cut, right? And then we said this is a hard problem, so let's relax the constraint and to have equation 22. Okay. And equation 22, it says minimization of F transpose LF subject to F transpose F equals 1. If you have watched the preliminaries that I asked you to watch, you would know that the result of this, which I will show you, the result of this optimization problem would yield to eigenvalue problem. Okay, eigenvalue problem, we'll see that. So what is, how do we solve this? Again, so hopefully you have watched the preliminaries, but here we have a constraint optimization problem, right? Here we minimize this objective function subject to some constraints. Okay. Now, if it was an unconstrained optimization problem, what would we do? Minimization of some function. We learned it in high school. What would you do? Take derivative, set it to 0, right? That's called first order optimality condition, right? So we would do that. However, now this is a constraint optimization problem. So what should we do now? Let's convert it to an unconstrained optimization problem. One technique to do that is Lagrangian. Lagrangian, denoted by this fancy L, is the most important function in optimization. Okay, and it is used a lot in machine learning. So its idea is simple. It says that put the actual cost function here, right? And then add the constraint with some weight to the cost. What is the constraint? Constraint was F transpose F equals 1, right? So I can bring the right hand side to the left hand side, everything to left, sorry. So it will be F transpose F minus 1 equals 0. So far clear? Now I want this to be 0. Basically, I want to minimize this part. So that's why I can add with some weight. I add this part to the actual cost, and then I minimize the whole thing. Okay. About the sign. So let me tell you that for proof, you can see my optimization techniques course. It has a long discussion. But let me tell you that if it is an equality constraint, as you see, the sign doesn't matter. The sign here doesn't matter. The sign behind the constraint in the Lagrange. It's either plus or minus. But if it is a minimization problem, not maximization, and it is less than or equal to constraint, then the sign must be positive. Okay. And you know that easily you can convert any greater than or equal to 2 less than or equal to by multiplying the size by -1, right? So far clear? So here we usually in machine learning, we have equality constraints. So that's why it's easier for us. Now, minus or plus, which one? Which one? Here is the practical part. You put the sign in a way that it suits your goal. If I put plus there, then if I take derivative and set it to 0, here at the end, I will have LF equals minus lambda F. And that minus would be a pain in the neck for me. Okay. That's why I put minus, so I don't have minus lambda F at the right hand side. Yeah.
Why does the sign end up matter? Can lambda not be anything? Is lambda constrained from some?
So no. For equality constraint, the sign of lambda is also doesn't matter. But for inequality constraint, the lambda must be greater than or equal to 0. By the way, the lambda here, did you understand the interpretation of the Lagrangian? Basically, I'm saying that rather than minimization of just the objective function, minimize the objective function and also the constraint as well. So both together, but they are not equally important. That's why I put some weight lambda. This weight, so the whole thing you can see it as a regularized cost function, and this part is a regularization part, right? And this is called regularization parameter, the lambda. But for Lagrangian function, this regularization parameter lambda is also called, it has 2 names: dual variables or Lagrange multipliers. Okay, so these simple weights that I talked about is called Lagrange multiplier or dual variable. Names are not important. Why do I say that? Because you will see that in the literature. You can call it Benjamin. But for the sake of literature, you should know that lambda is called Lagrange multiplier or dual variable. And Yes. So now what do? We want to minimize the Lagrangian. What was our optimization variable? It was f, right? It was f. So of course I should minimize with respect to f. And f is a vector, right? So what should I do? Take derivative of this with respect to f. So it will be derivative of a scalar, because Lagrangian is a scalar, right? With respect to a vector, it becomes a vector. Recall preliminaries. Okay, so now it will be 2LF. What is this? This part is quadratic with respect to f. It becomes 2LF, its derivative, right? And this part minus lambda f transpose f. This is also quadratic with respect to f. Its derivative becomes 2f. So I will have minus 2 lambda f. And the third part minus plus lambda will be a constant. It's constant with respect to f, so it goes away. Set it to the vector 0, right? So rearrange the terms. These two twos cancel each other. You will have lambda f equals LF equals lambda f. What is that? Recall preliminaries. That's an eigenvalue problem for the Laplacian matrix L, where f is the eigenvector and lambda is an eigenvalue, right? So now that's how we found it. So basically it says as equation 22 is a minimization problem, what should we do? You remember? Again, recall preliminaries. In what I teach, preliminaries are the most important part of the course, by the way, because I refer to them a lot. So as it is a minimization problem, how many, by the way, L Laplacian matrix is how many? I think it is n by n. Am I right? N by n. Because because adjacency matrix is n by n. So Laplacian matrix is n by n. How many eigenvectors will I have? N, exactly. And n corresponding eigenvalues. Agreed? So now what should we do? Which one? F is the eigenvector. Which eigenvector? I have n eigenvectors. I should take the eigenvector with the smallest eigenvalue, because it is a minimization problem. Right? Agree? But we know that the smallest eigenvalue is 0, and I should ignore that. I should ignore the eigenvector and whose eigenvalue is 0. I drop that, and then I get the second smallest eigenvalue and eigenvector, right? That would be my f. So according to then after finding this f, which is the eigenvector of the Laplacian matrix, what should we do? We determine the cluster of each point as this. So basically, if fi is greater than 0, it belongs to A, cluster A. If it's less than 0, it belongs to cluster A prime y. Because of this, recall the definition of fi, and we relaxed it to equation 21. So either look at this or this. The sign is important, right? Right? So now the question arises. What if we have more than two clusters? So far, we assume that we have two clusters, A and A prime, right? So let's talk about it. Extension of a spectral clustering to multiple clusters. So if we have more than binary clusters in data, the optimization would become this. What am I doing here? Rather than one single vector f, I'm putting a matrix f. Okay? So that's why I need trace, right? Because I want the objective function to be scalar, because f transpose LF is a matrix, okay? And we know that trace of f transpose LF is quadratic with respect to f. I have talked about all of these things in preliminaries. And so subject to f transpose f equals identity matrix, right? This time identity matrix. Now, so it's an extension of the previous optimization problem to multiple f's. Now I have multiple f's, okay? So what should I do? Again, you will see this pattern a lot, by the way. I have a constraint optimization problem. What should I do? I should convert it to an unconstrained optimization problem. How? By Lagrangian. So what is the Lagrangian? The cost, by the way, I think I have dropped trace here, sorry. Yeah. So what is constraint? Constraint is how should I call it? It's some restriction or constraint on the optimization variable. So basically, you're saying that you are not allowed to have to search in the whole space. You're only in some. You should search in some part of the space. Okay. For example, what does this mean? What does this constraint mean? It means that I want my matrix F the solution matrix F to be an orthogonal matrix. So only search in the cone of orthogonal matrices. You shouldn't go outside of them. Okay? You're not allowed to give me any F. Give me some F which is orthogonal. Okay. By the way, if I don't have this, maybe you are wondering why we have constraint here. Drop the constraint. What happens? Minimize trace of F transpose LF. What happens? Yeah, F will be 0. Because it's quadratic, it's like a bowl. Trace of F transpose LF, when does it become, when is it minimized? At the origin, when F is 0, right? Then it will be a ridiculous optimization problem. I need to say only search for orthogonal matrices, because a 0 matrix is not an orthogonal matrix. Yes. What is what?
What is making it an unconstrained problem? You said converting it.
Yes, so here, rather than this constraint optimization problem, I only minimize the Lagrangian without any constraint. So this became an unconstrained optimization problem. Agree?
So that still doesn't.
It doesn't have the problem of only minimization of trace of F transpose LFY, because it has this part. It has embedded the constraint inside the cost function as a regularization term. Okay. Now, what should we do? So, by the way, this is my constraint, and I know that I need to have inner product of the constraint with the dual variable. Do you remember? The previous slide, the constraint was scalar, the whole constraint. So inner product of a scalar with lambda became simple multiplication. Recall this here. Lambda times F transpose F minus 1. Basically, it was lambda transpose, but lambda is a scalar. But this time is a matrix, so I should say lambda transpose, but we know that according to preliminaries, inner product for matrices has trace. Okay. Basically, let me tell you this. Inner product always has trace. Why don't we mention trace for vectors? When I say X transpose Y, basically it is trace of X transpose Y. But why do I drop trace for vectors? Because X transpose Y is a scalar, and trace of a scalar equals itself. Okay. So now we have this minimization. So what should we do? It became a high school problem. Take derivative, set it to 0. You see, everything goes back to high school. So take derivative of a scalar with respect to a matrix is a matrix, right? And this is quadratic with respect to F, it becomes 2LF. And this is quadratic with respect to F, it becomes minus 2F lambda. Set it to the matrix 0. Rearrange the terms, these two terms cancel each other, we will have this. And what is this? This is again eigenvalue problem for matrix L, but this consider all of the eigenvectors and eigenvalues. All of the F is a matrix of eigenvectors whose columns are the eigenvectors, and lambda is a diagonal matrix whose diagonal elements are the eigenvalues, right? But I need to sort them. How? Because it is minimization problem, I sort the eigenvectors and eigenvalues from the smallest eigenvalue to the largest eigenvalue in ascending order, right? Because it's minimization. Okay, if it was maximization, I would sort it in descending order. Okay, so that's the thing. So we find F's, but again, we ignore the first eigenvalue with the the first eigenvector with the 0 eigenvalue. Okay, now if we have C number of clusters, now assume. So far I found the eigenvectors. Now I'm gonna use them. How? Here I explain. If we have C number of clusters, in general C can be any integer, right? Then we truncate the sorted F to have the C smallest eigenvectors with non-zero eigenvalues. What do I mean by truncation? So F, do you agree F is n by n, right? Because I have n eigenvectors each of which is n-dimensional. Okay. Now I only get the first C ones and drop the n minus C last columns. This is called truncation of the matrix. Okay. Basically, I make the square matrix a rectangular matrix. Yeah. Yes. You have a question?
So do we grab C minus one? Is it grab the C smallest then drop 0, or is it
What?
grab the C?
No, we get the C number of, so we truncate the sorted F to have the C smallest eigenvectors. So I get the C column, C eigen vectors, and drop the rest of them.
Okay.
By the way, I have already ignored the first eigenvector with the
Okay,
zero
ignore
eigenvalue.
0 first. We don't
Yeah.
ignore 0 second.
Yeah, I dropped the eigenvector. I don't consider the eigenvector with zero eigenvalue. Then I get the smallest C eigenvectors. When I say smallest C eigenvectors, I mean the C eigenvectors with the smallest eigenvalues. I mean that. Okay. So now F becomes n by C because I'll have C eigenvectors, each of which is n-dimensional, stacked column-wise, right? Now, after finding the matrix F, we treat the rows of F as new data points. That's beautiful. What does it mean? So, as you see, if you treat the rows of F as data points, because I have n data points, I have also n rows of F. But this time, if I consider the rows of the F as the new data points, that they would become C-dimensional rather than D-dimensional, right? So basically, we are reducing the dimensionality to C. Then in the new embedding space, which is C-dimensional, we apply another clustering algorithm, such as K-means, on the rows of F in order to cluster the endpoints into C clusters. Do you remember? We can use K-means to cluster data points into several clusters, K clusters, right? This time, I'm assuming now in my new embedding space, it is a C-dimensional space, right? I apply K-means, and I set K to be C. C number of clusters, right? So that.
Why do we choose that? Is it just arbitrary because it's been proven to work, or because why not choose K-means with any other?
So basically, if you apply K-means on in the input space, it is a regular K-means. But if you apply spectral clustering and then K-means, what happens? It is minimizing the ratio cut. So it projects data onto a subspace where the clusters get further from each other, get separated better.
Yeah, but why do we have to have the dimension that we're mapping to be the amount of clusters we want?
That's how spectral clustering works. That's how you're asking why the dimensionality of the subspace should be equal to the number of clusters. That's the question, right? I need to think about it. Thanks. That's a good question. I will think about it, and if I find the solution, find the answer, I will let you know in the next session. But yeah, I need to think about it. Okay. So that's good. So please ask me questions which challenge me. I like that. Okay. So the regular clustering methods such as K-means are applied on the input space, while a spectral clustering is applied on the embedding space of Y. In other words, the spectral clustering first extracts features for better discrimination of clusters, right? And then applies clustering. And why does it discriminate the clusters better? Because we minimize the ratio cut. You remember? When we minimize the ratio cut, basically we are finding the clusters which are away from each other. You may not understand how effective spectral clustering is. Let me tell you. Assume I have two clusters. Assume I have these things, okay? If you apply K-means on them, what happens? Two rings, basically. The K-means would say this is one cluster, this is one cluster, right? Because K-means is like Gaussian. If you set K to 2. Now, apply spectral clustering and let's C or K be 2, okay? Then it would say this inner ring is one cluster and the outer ring is the second cluster. So spectral clustering is obviously more powerful. Okay.
Where does it have value over the recursive methods? What sort of shapes would it?
You mean the DBSCAN?
Yeah, over DBSCAN.
So one benefit of spectral clustering over DBSCAN is that it is mathematically sound. And I believe that when something is mathematically sound is better. That's the thing. That's one thing. But it might have some other benefits. It might be faster. I don't know. But again, it depends on the number of points. Now, one flaw of the spectral clustering is it can't work for big data. Why? When I say big data, I mean I have the data points is large. Then n is large. When n is large, what happens? The matrix Laplacian matrix becomes large. Then you need to calculate the eigenvectors of a large matrix. You will get error in your computer. It either freezes or will say memory error, right? One problem with the spectral algorithms is big data. They can't handle big data. Yes. It depends on the CPU cores and the GPUs and the system that you have. But with the regular things, I think if you go more than several thousand, it will freeze. Okay. Yeah. So now in the original work of spectral clustering, this is approach 2. The following optimization problem was used. So the difference is that they put the degree matrix here in the constraint. Okay. Now, if we do that, what happens? The Lagrangian would be the cost, the actual cost, which has a trace, and this is the constraint. Okay. This is the Lagrangian, minimize it. So basically, it's an unconstrained optimization problem. Take derivative, set it to 0. Then you will end up with this. How is it different? What is this, by the way? This is a generalized eigenvalue problem, LD, right? Recall preliminaries. This is a generalized eigenvalue problem and not an eigenvalue problem anymore, right? So again, we sort the columns of the matrix F from the smallest eigenvalue to the largest eigenvalue because it's a minimization problem, right? Okay, acknowledgement. Some slides of this slide deck are inspired by our tutorial paper. See our tutorial paper for more details on Laplacian-based clustering and dimensionality reduction. This tutorial paper covers a lot of methods which use Laplacian in them. Laplacian-based dimensionality reduction, including spectral clustering, Laplacian eigenmap, locality preserving projection, graph embedding, and diffusion map. Okay, all of these use Laplacian. This is for more interested students. And by the way, as you saw, Laplacian clustering projects data onto a subspace, right? So basically, they propose an algorithm using Laplacian only for the sake of dimensionality reduction, and they called it Laplacian eigenmap. So it's inspired by spectral clustering, but for the sake of dimensionality reduction. Also see our book chapter on Laplacian-based clustering. So it's called Laplacian-based dimensionality reduction in our book. And some slides of this slide deck are inspired by teachings of Professor Ali Qudsi at the University of Waterloo. Also, we have spectral clustering in scikit-learn. What is scikit-learn? I think you already know what that is based on tutorials. So scikit-learn is a library in Python for basic fundamental machine learning. Okay, for non-deep learning machine learning. So we have that spectral, and it's easy. When you say spectral clustering, usually in scikit-learn, dot fit means train. Dot transform or dot predict is test phase. Okay, and fit underscore transform usually means train with this data and test on it. Okay, train on this data and also test on it. You got it. So these are the 3 main methods or functions in scikit-learn for different methods. And these are the references. Okay, so any questions?